Scientists can now image black holes directly, and the strangest part is that the biggest ones may be gentler, at least in one narrow sense, than the small ones. In the year 12,043, the Future Archives cataloged the Veyra Coil, a 2.4-meter guidance ring burned by particle abrasion on one face and polished on the other, recovered from a dead orbit around a quiescent supermassive black hole, which means the real question was never simply whether gravity would tear humans apart, but whether anything alive could survive the radiation, heat, and orbital precision required to live there at all. The Veyra Coil does not look like a machine built for wonder. It looks like a machine built for caution. Its outer surface is pitted on one hemisphere by high-energy particle strikes. The opposite face is smoother, backed for reflection and heat control. Along one fractured inner channel, the builders etched a warning in symbols, simple enough to survive almost 10,000 years. Inward drift was forbidden. That matters because it tells us what frightened them most. Not the abstract idea of a black hole, but a boundary in space where safe orbit became unsafe orbit. Recovered evidence like this can mislead. A future observer might assume the coil came from a doomed attempt to hover at an event horizon. The wear pattern argues the opposite. This component belonged to a habitat system, trying to stay well away from the worst environment, using orientation, shielding, and constant correction to survive beside a massive dark object. So the scientific question is sharper than the usual fantasy. Could humans ever live near a black hole if they respected the physics? Or does the surrounding environment make the idea self-defeating, even before gravity becomes the main threat? To understand what this records, we have to strip away one of the oldest black hole myths. People often imagine a black hole as a place where gravity is simply strongest at the edge, and therefore instantly fatal. General relativity says something subtler. The force that kills a body is not gravity by itself. It is the gradient in gravity across that body. The difference between what your feet feel and what your head feels. That is why mass changes everything. A small stellar mass black hole compresses its lethal region into a tight space. The tidal forces near its horizon rise so sharply that a human would be torn apart long before crossing safely. A supermassive black hole spreads that same horizon over a vastly larger scale. The horizon is bigger, and the tidal gradient there can be much gentler. This is one of the least intuitive facts in astrophysics. In one specific sense, the larger black hole is the less violent place to approach. That does not make it safe. It only shifts the danger. Once tidal destruction stops being the first problem, other constraints move to the front. Radiation, orbital stability, heat rejection, and the unforgiving geometry of relativistic motion. This is no longer a debate built only from equations. In 2019, the Event Horizon Telescope released the first horizon-scale image of the black hole in M87. In 2022, it did the same for Sagittarius A seas at the center of the Milky Way. These were not direct photographs in the ordinary sense. They were reconstructions from a planet-sized network of radio telescopes, combining signals with exquisite timing to resolve structures on scales once thought unreachable. That achievement changed the conversation. Black holes are not just inferred from missing light or from stars whipping around invisible masses, though we have that evidence too. We now observe environments at the scale where gravity shapes the last bright material before disappearance, and those observations agree remarkably well with general relativity. The archives preserve this as a hinge in human understanding. Once our species could image horizon-scale structure, black holes stopped being purely theoretical destinations. They became mapped environments with measurable constraints. That is a crucial difference. Engineering begins when myth gives way to parameters: mass, spin, accretion rate, jet orientation, particle flux, orbital radius. A habitat cannot be designed around awe. It has to be designed around numbers. A black hole can be quiet in one way and murderous in another. Established physics tells us that Hawking radiation is not the practical problem for astrophysical black holes. For stellar mass and supermassive black holes, that radiation is negligible. These objects are colder than the cosmic microwave background. They absorb more energy from their surroundings than they emit thermally. So, if a black hole habitat fails, it does not fail because the hole is glowing with exotic quantum fire. It fails because matter falling toward black holes can become unimaginably hot. Gas spiraling inward forms accretion disks. Friction, compression, and magnetic turbulence heat that matter until it shines in X-rays and beyond. Some systems also launch relativistic jets, narrow beams of accelerated particles and radiation that can remain dangerous over enormous distances. That is the reframe the Veyra coil seems to confirm. The central mass was not necessarily the immediate killer. The environment around it was. A dormant or weakly accreting supermassive black hole is therefore the only serious starting point for this discussion. Not a quasar, not a blazing X-ray binary, a quiet giant, one with enough mass to soften tidal forces, and little enough feeding activity that shielding becomes merely extreme instead of impossible. Even a quiet giant does not let you park wherever you please. Black holes have a fundamental orbital boundary called the innermost stable circular orbit, or ISCO. Outside that limit, a circular orbit can persist. Inside it, small disturbances no longer damp out into stability. They grow into an inward plunge. For a non-rotating black hole, that boundary sits at 6 gravitational radii. For a rapidly spinning Kerr black hole, prograde orbits can move closer. That sounds like an invitation to approach the horizon. In practice, it is a warning. The closer a habitat moves inward, the less room it has for error. Navigation margins shrink. Radiation typically rises. Relative velocities grow. Any station-keeping failure becomes harder to correct because the orbital landscape steepens. The engraved unequal timescale on the Veyra coil suggests its builders tracked another effect as well. Gravitational time dilation. Clocks deeper in the well run differently from clocks farther out. That is real, measurable physics. But time dilation is not a magical advantage. It complicates communication, logistics, maintenance schedules, and political coordination long before it becomes useful as a cultural dream of living slower than the outside universe. A black hole habitat would not just need to survive, it would need to remain synchronized with a civilization living elsewhere. The asymmetry of the Veyra coil reveals a design logic that present-day engineers would recognize immediately. If one face endured the particle storm and the other supported reflection and heat shedding, then the habitat it served was probably not exposed uniformly. It likely lived in a deliberate geometry, shield toward the source, radiator toward the dark. This teaches a hard engineering lesson. In deep space, survival is often a matter of where you let energy go. Near a black hole, every protective choice creates another burden. Thick shielding adds mass. Mass demands propulsion and structure. Power systems create waste heat. Waste heat must be radiated away, but radiators themselves can become vulnerable surfaces. A settlement may survive the radiation only to choke on its own thermal load. That is why some theoretical studies imagine humans staying far from the dangerous inner region, while machines, mirrors, and sensor platforms move closer in. The phrase living beside a black hole may be misleading from the start. The realistic version looks less like a city on the edge of a glowing abyss, and more like a sparse orbital network built around shadows, exclusion cones, and sacrificial outer layers. If you're enjoying future archives, subscribe. There's another investigation waiting beyond this one. There is one reason civilizations might tolerate all of this difficulty. Rotating black holes do not merely sit there, they drag space-time around with them. In the region outside the event horizon called the ergosphere, physics allows energy extraction in principle. Roger Penrose described one version decades ago. Modern astrophysics also studies how magnetic fields and plasma around spinning black holes may tap rotational energy and help power jets. This is established science at the level of mechanism. Black hole spin can, in principle, be part of an energy source. What is not established is the human engineering leap. No one knows how to turn that into a safe habitat-scale power system. The same plasma structures that make spin extraction interesting also make the environment unstable, hot, and difficult to control. A civilization might exploit that energy remotely while keeping people far away. So, here the future branches. One path is a black hole economy without black hole neighborhoods. Autonomous industrial swarms operate in the inner danger zone while human communities remain distant. Another path is that the maintenance burden becomes so severe that even the power advantage loses to easier options like starlight harvesting, fusion, or industry around less hostile compact objects. By this point, one possibility can already be discarded. Humans are not going to live beside an actively feeding black hole with anything like present-day technology. Current materials, shielding, propulsion, thermal management, and closed life support systems are nowhere near sufficient. Observatories continue to show that accreting black holes can flood nearby space with X-rays, gamma rays, hot plasma, and fast particle streams. Against that environment, courage is irrelevant, so the serious case narrows to a much less cinematic target. A comparatively quiet supermassive black hole, probably far from any bright inner disk, with habitats on carefully chosen inclined orbits and most dangerous operations delegated to machines. Even then, the Veyra coil warns against romanticism. Its etched clock scale implies relativistic bookkeeping. Its cracked superconducting traces imply repeated thermal stress. Its abraded face implies a particle environment harsh enough to grind away outer layers over time. In other words, the artifact does not say humanity conquered black holes. It says that if humans ever lived near one, they did so by accepting a civilization built around caution, redundancy, and distance from the very thing that drew them there. And that leaves the real debate for what comes next. Once gravity stops being the first obstacle, which cost actually breaks the dream first? A strange thing happens once shielding enters the picture. Protection starts creating a second problem. A habitat near any strong radiation source needs thick mass between people and danger. Rock, water, metal, hydrogen-rich layers. Something heavy enough to stop particles and absorb X-rays. But absorbed energy does not disappear. It becomes heat, and heat in space is awkward. You cannot dump it into air or water. You can only radiate it away. That sounds simple until the numbers turn ugly. The power a radiator can shed depends strongly on temperature and area. If a habitat insists on staying near ordinary human temperatures, the radiator area grows fast, very fast. A station that survives by swallowing incoming radiation may then need structures far larger than the living volume just to glow that waste back into space. This is one reason active black holes are such poor neighbors. The hazard is not only that they shine in X-rays, it is that every shield, every powered magnet, every superconducting loop, every life support system, and every correction burn adds to the thermal bill. The Veyra coil carries this clue directly. One face is roughened by particle damage, the other is smoother and backed for reflection and thermal rejection. That asymmetry suggests a civilization that oriented every component around a simple rule. Take the hit on one side, dump the heat from the other. So, the engineering question sharpens. Not, can gravity be endured? Can a habitat remain cool while everything around it tries to turn shielding into an oven? The etched clock scale on the coil may be the most revealing mark of all. General relativity predicts that clocks run differently in stronger gravity and at higher orbital speeds. Near a black hole, both effects matter. A station deep in the gravity well can experience less elapsed time than partners farther out. That is established physics, but it is often misunderstood. Time dilation is not a free benefit handed to the people closest to danger. To gain a large effect, the habitat usually has to move deeper into exactly the region where radiation, orbital instability, and heat become harder to manage. The same orbit that makes one clock lag behind another may also demand exquisite navigation, relentless forecasting of plasma conditions, and constant agreement on whose clock defines on time. That sounds philosophical until you turn it into logistics. Deliveries arrive according to one schedule. Maintenance windows are calculated in another. Messages to distant settlements accumulate coordination offsets. Biological lives, legal contracts, and machine control loops stop sharing a single ordinary rhythm. The coil's unequal clock intervals suggest this was not a curiosity. It was operational. Someone needed conversion scales built into hardware because relativistic bookkeeping was part of daily survival. Here, the future branches again. One possibility is that black hole habitats become prized for physics, computation, or long baseline timing experiments. Another is that time dilation never becomes useful enough to justify the political and ecological complexity it introduces. The romance says time itself becomes a resource. The artifact suggests it first becomes paperwork with teeth. The most plausible target in this entire discussion is not a feeding monster. It is a quiet giant. A quiescent supermassive black hole changes the problem because the horizon can be large, tidal gradients can be milder, and the surrounding environment can be far less luminous than a quasar. Sagittarius A. In the Milky Way is often used in thought experiments for exactly that reason. Compared with active galactic nuclei, it is dim. Dim does not mean safe. Galactic centers are crowded places. Gas clouds drift. Stars shed matter. Magnetic fields twist. Compact remnants pass through. A black hole that is calm on one time scale can flare on another. Even Sagittarius A shows variability. The broader lesson from X-ray and radio astronomy is that accretion is not a neat on-off switch. It is episodic, turbulent, and capable of surprise. That matters because a settlement built around a quiet environment may fail not during normal operations, but during reactivation. A fresh stream of infalling matter could brighten the inner region, harden the radiation field, and force every shield margin to prove it was not optimistic. Now the Veyra coil's warning band starts to read differently, not simply stay outward with reserve. A black hole habitat would not just need a survivable orbit, it would need evacuation geometry, dormant safe sectors, and the ability to endure environmental change without assuming the central engine will remain polite forever. So, one strong future path survives. Around a dormant giant, yes, but only if dormant is treated as temporary, not permanent. By this point, a pattern is hard to ignore. The closer the useful energy lies to the black hole, the less likely humans are to stand next to the machinery extracting it. That pushes the most credible future toward division of labor. People stay far out, where shielding, ecology, and temperature control are merely difficult. Machines go inward, where repair rates are brutal but tolerable for systems that do not need sleep, air, or a biosphere. This is not science fiction decoration. It follows from a basic economic fact. Human habitats are fragile because they must protect everything at once: bodies, crops, water cycles, electronics, and social continuity. Industrial swarms protect only function. If one collector, mirror, or plasma coupler fails, it can be replaced. If a habitat fails, the whole experiment may end. That makes the phrase black hole city increasingly misleading. The more realistic picture is an anchored civilization with a forbidden interior, a machine zone feeding power, data, or scientific access outward. And now the Veyra coil looks less like a relic from the center of activity than a border instrument. A guidance ring, a device that helped one station hold position relative to shadows, exclusion wedges, and service traffic arriving from safer distances. In that interpretation, the artifact does not commemorate triumph at the edge. It records a boundary. The future settlement that works best may be the one that admits humans were never meant to occupy the innermost profitable region at all. They were meant to orbit the infrastructure that did. A small outpost and a real settlement are not the same achievement. That distinction may decide everything. A research station can survive on narrow margins. It can import rare components, accept limited crew, operate with heroic maintenance, and justify itself through science alone. Human history already knows how to build exceptional places that are not easy places. Cities obey a harsher standard. They need spare capacity, redundancy that is affordable, not ceremonial, industry nearby, children, agriculture, replacement parts, waste handling, social stability, and failure modes that do not cascade through the entire population. Near a black hole, each layer scales badly. More people mean more heat. More habitat means more shielding mass. More shielding mass means more structure and orbit control. More infrastructure means more exposed surface for particle damage and more thermal systems to keep within limits. That creates a trap. The first crewed installation may be barely possible, while the 10,000th resident is what breaks the concept. This is why the scientific outpost, not city pathway, remains so strong. The black hole may host observatories, timing laboratories, or remote energy control hubs for long periods without ever becoming a major home for human population. The The Veyra coil fits that reading uncomfortably well. It is sophisticated, yes. Durable, yes. But it is not lavish. It looks like hardware optimized for survival in a place where every kilogram argued for its life. Some futures fail because they are impossible. Others fail because they never scale beyond the elite outpost stage. To judge a black hole habitat honestly, it is not enough to ask whether it can be done. We have to ask what it is competing against. A civilization with the power to build near a black hole would almost certainly also know how to build vast free space habitats, harvest starlight over enormous areas, run advanced fusion systems, mine compact objects, and position industry around far quieter energy sources. Those alternatives matter because engineering chooses not the dramatic option, but the cheapest resilient one. Starlight is weak compared with the violence of accretion, yet it is predictable. Fusion demands difficult confinement, yet it does not sit inside a relativistic hazard map. Even neutron stars and white dwarfs, dangerous as they are, may offer some industrial advantages without the same combination of orbital bookkeeping and deep gravitational penalties. So, why go to a black hole at all? Perhaps for unique science, perhaps for prestige, perhaps because a rotating giant offers unusual power density, perhaps because in the far future, when stars age and priorities change, black holes become more attractive than they are now. But that remains informed speculation. The stronger present conclusion is sharper. Black hole living does not merely need to work. It needs to beat rival futures that are easier to build, easier to cool, easier to navigate, and easier to repair. That is the strongest argument for the radiation wall view. Not that black holes are forbidden by physics, that they are defeated by competition. By now, the artifact can be read with more discipline. The Veyra coil does not prove that humans hovered near an event horizon. It does not prove a vast black hole metropolis. And it does not prove that spin extraction ever powered daily life on a grand scale. What it does constrain is more subtle, and perhaps more important. Its shielding beads indicate long exposure to a harsh, high-energy environment. Its superconducting channel shows repeated thermal cycling. Its particle scars are directional, not random. Its engraved wedges encode safe and unsafe sectors. Its clock marks imply routine relativistic offsets between local operations and a distant reference frame. Taken together, those clues support one coherent explanation. If humans ever built beside a black hole, they did so in a quiet supermassive system, at significant distance from the inner disk, with strict orientation control, heavy thermal management, and constant respect for changing radiation geometry. In plain terms, this was not a monument to boldness, it was a tool for caution. That is the deepest twist in the object. Popular imagination expects the black hole itself to be the enemy. The coil says the real enemy was the environment around it. The particles, heat, timing offsets, and orbital margins that slowly wear down any claim of mastery. So the recovered evidence has now answered the opening mystery. Black holes may not be uninhabitable because gravity makes them impossible. They may be unlivable at scale because everything required to survive nearby becomes an endless bill. So, where does the balance of evidence land? On the most plausible path, humanity never truly lives beside an active black hole. Instead, it builds around a dormant supermassive one, far out, heavily shielded, thermally burdened, and operationally dependent on machines closer in. The settlement is sparse, specialized, and always one environmental shift away from proving too expensive. That reading explains the Veyra coil. It also leaves one serious rival view standing. The rival view says even this cautious version gives away too much. Too much shielding mass, too much waste heat, too much orbital discipline, too much dependence on a central object whose surrounding environment may change without asking permission. In that view, black hole habitats remain prestigious experiments or failed ambitions, while the real future belongs to quieter stars and colder artificial worlds. And that is the debate the artifact cannot settle for us. If humanity ever tries this for real, which limit breaks first? Not the headline version, not gravity versus courage. The real scientific question is whether the first fatal cost is radiation shielding, waste heat rejection, or the energy needed to maintain a stable habitable orbit over centuries. The Veyra coil survived long enough to suggest that someone thought the answer was manageable. Its damage suggests the margin was never generous. Let me know in the comments which assumption you think this future depends on most.